So why don't I get started on this? So I wanted to go through, so the homework's on this paper by Jorge. So Jorge is from Budapest, right? So like this is 88. He references this is reference 88 in the paper, but it's when he was at this university in Budapest. And then he went to can you guys hear me? Inakuba, can you hear me?
Yes, Prof.
Okay, all right, that's good.
Yeah.
So anyway, he was in Budapest and he did a lot of work on gels. And then I think it was kind of linked in with Degens, who was won the Nobel Prize for polymers and this kind of scaling theory, the kind of power law things. And yeah, Jorge had something to do with Degens. He cites Degens' book in this paper. So anyway, this paper is for the last figure in it, where he gets the data from this the scaling behavior of the modulus of gels. And then he went to NIST, and he worked at NIST for a while. Jack Douglas is from NIST. He's like the senior simulation and kind of theory person at NIST in the polymer division. NIST is a national lab in DC. It's like the science lab for the US, basically the one that, so the science in the US is divided into the Department of Energy, which is kind of nuclear weapons, the Department of Defense, which has like 3 national labs, like the Air Force Research Lab in Dayton, and there's a Navy Research Lab in DC, and the Army has some kind of research labs too, right? So anyway, and then NIH is a health, it's like medical research labs. So NIST is kind of like the non-military, non-nuclear energy science of the United States, right? So Douglas is a kind of the leader of the simulation stuff for polymers there. This is, I don't know who Kremos is. Sounds like a Greek person. And Vassar is also at NIH. So Jorge was at NIST and then moved to NIH, doing like gels for bio applications, like drug delivery type things. And then Vassar, I guess, I don't know who Vassar is, but he's also at NIH. So I think they work together. So anyway, so they did a simulation. So they have, and so Jorge has been working in gels for a long time. These are like gels, real gels, right? And then, in other words, this is a simulation of gels. So he's got the 612 potential with some added energy, and then it's kind of typical things here. So the 612 potential has an energy well, so he adds in a parameter where he can tune the well depth and not affect this term, right? So this just has the energy for the 612. He throws in this square well potential that shifts basically the depth of the well. So he pieces together a potential for how, so this is the distance between 2 particles in the system, 2 beads. And then this is the potential and the distance. Sigma is the diameter of the bead. Then this is their preferred separation distance. So you want to minimize the energy. So you find the minimum, that's what they would go to. Right, and then it goes to 0 at long distances, and then it's short range repulsive, right? So that's kind of a typical potential curve, but he tunes the depth of this well with this lambda, and then all right, so he's going to make this thing. Okay, so he's going to make these, and he's going to make one of them, but he's talking about many of these. So this would be like a drug delivery device, and it's composed of 4-arm stars. So he's got the circles around the 4-arm star. It's got 4 arms, molecular weight M, so there's 2M between the crosslink points in the network. And the thing's going to be, it says here what it is somewhere. So he's got NB is one of these arm lengths. So there's 2 NBs to go across it, and then functionality times the molecular weight of one of those arms is 4 times that plus 1 for the center bead, and then times NB cubed is going to be how many crosslinks there are in the gel. And so his thing ends up being that this thing has 101,000 molecular weight, which is typical for a normal polymer, right? That's like a normal polyethylene would be something like that. So it's not a huge molecular weight. The chains are pretty much confined with this crosslinks, right? And then he's going to change this potential to allow the thing to swell and deswell. So you can see like how the size of this thing changes. And he's also going to change the concentration and see what impact that has on it. That's kind of where he's coming from. He correlates this lambda, so he can calculate the rates of gyration according to the temperature. And then he can also, race gyration also changes when he changes this well depth, like when he changes this lambda. So what he does is he changes lambda and he measures the race of gyration of this whole thing, of this blob thing. And then basically measures the ratio versus that, and then comes up with an empirical function. He makes up a function that this lambda is going to be 1 over temperature. So if the temperature goes up, it's as if the well gets smaller, right? Because the temperature is going to be compared to this potential. So if you have a higher temperature, it's easier to overcome the potential, or if you reduce the potential, it's easier to overcome the potential. So because of that, and higher temperature would equate to smaller potential. So there's an inverse relationship. So it should be 1 over T is lambda, right? So that's kind of the idea here. So with that, he can say, he can plot a function of lambda and T. So he had, so you can go and say like we had 1/2 minus chi, right, is B2, is our second virial coefficient. And then for the oops, there. So for the osmotic pressure, so he's measuring osmotic pressure on these things. We have the Florey-Kriegbaum approach is that you have the osmotic pressure is going to equal like KT over the volume of one of these, the beads that make up this star thing, that makes a network, right? So, and then KT, and then 1/2 minus chi is per bead, per elemental unit. And then that's times phi squared. So that's why it's B2. And then this, the first term in this is phi over n. Oops, sorry, forget about that. Plus, like that, right? So basically that's, so you can do something like, you could take out the n, you could take out this whole prefactor and say you had V pi over KT.
Prof,
Yeah.
apologies, we can't see what you're writing.
Oh, shoot. All right, so sorry about that. Thanks. So this is the Florey-Kriegbaum. Let me write that better. So pi equals KT over V0. V0 is the bead size for these star things. And then phi over n. So the first term is, this is basically the ideal gas, like PV is RT. So phi's number per volume. And then for the first time we do per number on this thing because it's a polymer, because you're talking about each of these gel things would be one thing, right? So this is number of Mur units. Number of Mur units divided by the 101,000, which is n, gives you how many of these blob things, how many of these gel blobs that are floating around. And you're talking about pi of the gel blobs. So with osmotic pressure, you're talking about always the number of these things that are floating around, the chains that are glued together, right? So this, in this case, it's a square gel blob. So it ends 101,000, and then phi is the number of Mur units, the number of beads per volume, right? So anyway, and then so that's the first term of this thing, plus 1/2 minus chi is the B2, the second Bureau coefficient, times the composition squared. That's the Flory-Krigbaum function that we had before this thing, right? So anyway, so going back to that paper here. So what was the point of that? I don't remember. I lost track. Sorry. Anyway, so that's what he's doing. He got because of this temperature. So basically, if you say this B2 is 1/2 minus chi, is 1/2 minus chi, and chi is the coordination number around one of these bead sites, like it would be 6 if it's a Cartesian, times the average energy of interaction of attraction between beads. So the polymer, and then the solvent. There's an implicit solvent here, means there's no solvent. So it's just polymer, and then polymer minus 2 times polymer solvent, this average energy, and then divided by KT, so per bead, right? So that means that this thing, B2 is actually like 1/2 minus some number over T, right? Because chi is something over T, like just call that B, call K Z, that's all B. And then if you wanted to say that at the theta condition, so theta equals T, then B2 goes to 0 at that point. So that means that theta has to equal B over 2B, 2B, right? 2B theta equals, if this equals 0, then the temperature at that point has to equal 2B2, right? So you have that kind of expression. So then you can go back and say that this is theta. So then you can write the condition of where B2 0 equals 1/2 minus so B2 would be theta over 2 temperature, right? So you can rewrite this thing like that, and then you can multiply by temperature over temperature. So that equals temperature minus, so you have 1/2 times temperature minus theta over temperature, right? So you can convert this 1/2 minus chi into this temperature thing, right? And then if you say that, well, lambda goes as kind of 1 over temperature, right? So I can say that lambda theta equals 1 over theta. So then you can just plug into this thing. Then you can plug into that thing that your condition for the theta condition is going to be that 1 over lambda minus 1 over lambda at the theta condition over 1 over lambda. That has,
Professor, we cannot see.
oh, sorry. Right, so if you say that T, so that if lambda is 1 over T and lambda theta is 1 over theta, then you can plug in like 1 over, and the 2, it equals 0 at the critical, at theta temperature. So you just plug in like 1 over lambda theta, 1 over lambda, then multiply everything by lambda. So you have 1, see, multiply everything by lambda. Yeah, you have 1 minus lambda over lambda theta over 1, and then multiply everything by lambda theta. So you have lambda theta minus lambda over lambda theta. Right, so that thing, so you have T minus theta over T, or lambda theta minus lambda over lambda theta. Those are both equivalent to 1/2 minus chi, like B2. Right, so this is something that's pretty common in the literature to do this. So he does that, just got that T minus T theta over T, and you get lambda theta minus lambda over lambda theta for the plots here. So when that equals 0, that's where you're at the theta condition. Right, so everything gets to be in this other nomenclature. this defines a critical point for the Gaussian chain. Same here. All right, so there's a lot of things like that in here. So basically you have to kind of work through those to figure out what's going on. So he's got that, and then his first condition, his first problem. So he says like he can show that there's this functionality between these, and that's where he kind of gets that. So basically, it's lambda is 1/t. That's kind of the idea. There's some other constants here, or you could do a power of t to get it to look better, but basically that's pretty good. Like the circles are this more modified one, and the x's are this one. Anyway, so that's something that he's doing here. And then so the race gyration he's talking about is race gyration for this whole blob thing, right? So we had in class, we went through this the radius of gyration stuff. Should be kind of here somewhere. Just to see, I think the recent gyrations in here somewhere. I forget what it was. I lost that sheet. I think it was 52. But yeah, race gyration. So I think we said what it was. Like basically, so slide 50, I guess. So you calculate the center of mass of the object, and then you're going to take every position in the object and subtract that from center of mass and square that and sum those up and divide by the number of beads in the gel. Right. So you can get a race gyration for anything, any object. Right. And it turns out if you plug in that NL squared is the distance between 2 points in the polymer, then you'll find out that the race gyration for polymer squared is the end-to-end distance, the NL squared by 6. So 2.45 RG is end-to-end distance. So RG is smaller than the end-to-end distance for a linear polymer chain that's Gaussian. So NL squared means it's Gaussian. The end-to-end distance, sorry. The end-to-end distance R equals 2.45 times this race of gyration number. Right. And again, you can get the race gyration from a scattering measurement or something. So he's talking about this number. So the reason to go to it here, or one reason to go to it is that, so if you have this weird gel thing, so that's your object. And then like, what's the end-to-end distance? Like there is no end-to-end distance. I mean, you could say this is an end, that's an end. So that could be an end-to-end distance, or this to that, right? There's a lot of ends here. So there's no end-to-end distance. But there is a race gyration that you can calculate by this same function, this summation of from the center of mass of the blob to the position of each bead, square it, and then square the difference, and you can get this race of gyration. So it's going to be smaller than the size of the object, right? So basically there's an issue. So he's using like the volume of this object is RG cubed. Right, but we know RG is kind of like 1/3 of the actual size of the thing. So this is going to be an underestimate of the size, right? If it's a fractal object, which it is, then it'll be an underestimate to get the race of gyration. Anyway, so that's kind of one part of this thing. But it gets the same behavior that we got before. Like in other words, when we looked at how the race of gyration changed with temperature for polymers, that is up here, oops, there. So we got this kind of behavior, like as the temperature goes up, we get this kind of swooping curvature, and that thing can be explained with this Flory-Krigbaum equation. This thing will explain the shape of that curve. Right, so we already have an equation that describes swoopy curve like that. And then he's going back to, this is the same swoopy curve, right? It looks almost the same, but he doesn't use that Flory-Krigbaum equation. He invents some equation, some crazy equation, because the thing isn't Gaussian, right? This Flory-Krigbaum, so this Flory-Krigbaum analysis that we did in class, that relies on a Gaussian chain in the, oh, this is slides 3. I wanted slides Here, it's the beginning of this thing. So that relies on the chains being Gaussian. The first step of this derivation, first step that you do is you say, well, this first term is Gaussian. That first term is because NL squared, that term means Gaussian, right? It means it's a random coil, fractal dimension 2. And then you add in perturbations to that end up giving you the fractal dimensions 5/3, 1.67 by the Flory-Krug approach. But the first step is to say that the thing's Gaussian, right? So his thing's not going to be Gaussian ever. Like when he's in a theta state, this is not going to be Gaussian, this network of these chains. So it's got to be, so if you say you have a randomly, so if you say you have a randomly branched Gaussian chain, then commonly people say the fractal dimension is 2.5. So you go from 2 to 2.5. That means that, so they talk about nu is 1/2 is 0.5. Then for a good solvent, it's 0.588. And here this thing's going to be, nu's going to be 1/2.5, which is 2/5, or 0.4. Right? So this is for a Gaussian, or for a theta random branched chain. And he uses that number, this 2/5 number, to talk about what this thing would be at the theta state. So the importance of that is he needs to determine what theta is and what lambda theta is. And one way he does that is he says he has that Rg is going to go with the molecular weight to this nu, or to 1/df. In other words, Rg to the df equals m. So Rg goes with m to this nu, right? And the nu that he uses is this 2/5 number, right? And he says because once any chain of any molecular weight, if it's at the theta condition, so it's at lambda theta and t theta temperature, then it has to follow that law. Then he can plot these RGs. Let's see, where's that plot? It's early on here. Well, see, he's plotting Rg divided by molecular weight to this nu, and the nu is this 2.5 number. So 2/2 is the dimension. He's using a random coil number. Then he's plotting it against this thing. This thing is really 1/2 minus chi in terms of lambda. And he finds a point where it doesn't change. He says that's the theta point. So then he defines his lambda at that point is lambda theta. So he finds out that lambda theta is 0.7 for his blob thing. And then lambda theta for a Gaussian chain is like 0.72 or something higher. That means it's t, because lambda is 1/t, t theta, or theta is theta for the blob is less than theta for a Gaussian chain, which makes sense. When you connect the thing together, it becomes less soluble, so the temperature of phase separation drops. Right, so that kind of makes sense. So everything kind of makes sense here. I mean, just thinking about it. And he shows like he can normalize Rg by Rg theta, and then and by this chi minus 1/2 minus chi number, and then with this molecular weight scaling factor, and you can get all the curves for different. What is this? Different, I guess, different topologies, like different number of branch points going in one direction. So twice as many or half as many, then different molecular weights of the arms of the chain. So, and everything follows a universal curve if you plot it in those conditions. So let's see. So that's part of it. There's a lot in this paper. A lot that you'll have to dig around to figure out. There's some, all right, so there's some things like this is a pretty good thing to look at the definition of the second virial coefficient. So at first they say, like, for an ideal gas, P is rho KT, and then you add in this viral expansion to get the second and third viral coefficients. Right, and then this is some book thing. It's linked on the under the homework. And then there's ways to calculate this B2 from the potential between units in whatever it is you're looking at. Right, so this is a potential, the attractive potential between things in the system. So if you integrate this Boltzmann factor, the potentials -1, this gives you the viral coefficient, right? And there's a volume here, 4 pi r squared dr gives a volume, right? So that thing's kind of a basis for figuring out like what, because he's got potentials he's putting into a simulation, and then this is how you'd get the viral coefficient from the potentials. It's one way to get it, right? So so if you calculate the viral coefficient that way across different conditions of lambda, then you can find out where the viral coefficient goes to 0, and you can find the theta temperature from that. You find the lambda theta temperature, the lambda theta value from that. If you do this calculation for every different lambda, then you find the point where that thing goes to 0. Where is that plot? Something goes to 0. Anyway, he does that and he finds where it goes to 0. And then that's his, that's the second way that he gets, it's in part C here. Osmotic pressure by the calculation. So he's doing this integral. F of r is this exponential -1, the same thing as this thing. And then integrate that thing, r squared dr. Calculate that for different lambdas, and then find where it goes to 0, and that gives you your theta condition, right? So he does that. I mean, he defines the theta condition in 2 ways. One, he uses this scaling thing, this business, and finds where they all collapse to the same point. And then secondly, he does it by this calculation of the viral coefficient, finding where that goes to 0. So yeah, there's a lot in here. I mean, but these are all classic standard things, you know, there's nothing nuanced about this. This is something that's interesting. Like he's got the size of the blob, right? And then so the size of the blob at low composition should just be constant because the blob is independent, right? In other words, if you're at low compositions, so you have this blob thing, and if they're isolated, it doesn't matter what concentration you have. If they get a little bit more concentrated, it doesn't matter until they like touch each other, right? So that's the C star, and here so C star if you're doing an experiment, and rho star if you're doing the simulation. It's like the density star, not 2, right? And that's going to be the mass of his coil, this 101,000. And then divided by Rg cubed, whatever you calculated for Rg for that thing. That gives them this rho star number. Right, so once you get to concentrations below, if you're below rho star, the size of the blob doesn't change any. So that's below rho star, nothing's happening. Then when you're, supposedly when you reach 1 for rho star, then you would see some kind of change happening. Right, so the size gets smaller because the things are becoming compressed. So the reason that it goes 1/3 is that this thing has a volume of Rg cubed, right? And if they're polymer chains, then when they reach this overlap concentration, they can intertwine with each other. They can occupy the same space because there's space in between, right? But if it's this blob thing, right? This thing is showing a picture of wherever here. I mean, this thing can't intertwine. There's no way to overlap 2 of these because they're just impenetrable, right? I mean, a little bit at the surface, but basically can't get inside of it with another blob. Maybe a single chain could get inside of it, but another blob can't, right? Another blob is stuck. It's just hits it. So if you increase the concentration past that, you just have to squish the blobs. That's all you can do, right? And that means that that the volume, so this density is going to be the basically 1 over the volume, and the volume's basically 1 over RG cubed. So if you increase this has to drop by the power 3, just because they can't penetrate each other. So he shows basically that they can't penetrate each other by this 1/3 power law to the raised gyration. It's a log plot, and the slope is 1/3 here. All right, so that's kind of the game he's playing, and it works. Like he gets that. So he reduces RG by the dilute one, the plateau one, so it equals 1 when it's a dilute. And then there's this nuance that like it doesn't start to do this decay when you reach RG squared, right? Because RG isn't really a measure of the size of the thing. In other words, RG for a coil is going to be the coil size by 2.45, like smaller. It's smaller than the coil. So RG cubed isn't going to be the measure here. Like where it's 1, that's already much smaller than one of these blobs. The blobs are larger than that, so the density would be lower when it actually starts in. So that's why 1 of this, usually 1 would be where you'd see the tail over, but because he's using RG, this doesn't work out. Right. So basically the tail over is somewhere over here, and that's the actual size of the blob, would be like the density related to that size. Cube root of the density would give you kind of the actual size of the thing. Oops, what did I just do? That was pretty weird. Did something, I right clicked to make, I did something weird randomly. Anyway, so that's the idea of that 1/3 in that plot of the RG versus the density. What else is in here? So there's a lot in this paper. Okay, then he gets so there's a plot here, this plot, right? So he's got this weird looking plot. Okay, so so he's got these 2 axes on this thing, right? This MW pi rho, all this business, right? So so you can figure that out by going back to the this expression we had before for the osmotic pressure, which is in number 3, right? Page like 16, I think, something like that. Oh, it's 26, I guess. No. There's osmotic pressure here. So we had where's the fluorine one here? I mean, that's kind of the fluorine one. So you have osmotic pressure divided by KT, and then we can divide by rho. So if you take rho here and divide, and then take n and multiply, right? So you have divide by rho, multiply by n, then the first term is going to be 1, right? And the second term is going to be B2 times rho. And because you multiply by n, you have to multiply that guy by n also. Right, and then let's see. NB2 rho, I think that's it. So then go back to this. So here I have molecular waves, n times pi divided by rho. N pi by rho. And he's changing KT here. He's changing the lambda. So that's n pi by rho. And then this MB2 times rho is because of this. So he's got MB2 rho for the bottom part. So he's just shifted the things around so that he can get it into this form. So basically, if this was ideal, then that thing would just be like 10 to the 0 is 1. So it'd just be 1 if it's ideal. And then not ideal, it shoots up, right? It goes up. So because it's got this second Viral coefficient. So if it was just a second Viral coefficient, then this would be rho would be power 1. So you'd see this is rho at the bottom, so this would have a slope of 1, so kind of 1 decade. So if the way my arrow's going, like basically 1 decade here, 1 decade here, so you'd have that kind of slope, right? And his slope here is much steeper than that. So he shows that dashed is flexible chains So that's his row 1 out here. That's a slope of 1. And his data is steeper than that. But it's not as steep as hard spheres, which I think is a slope of 3 or something. So anyway, he can calculate it for randomly branched chains, and he gets this dash thing, which is basically the star polymers, and that matches up with his data pretty well. So he's kind of happy with that. To get that, in order to get that odd number, he goes to the third Ferrel coefficient. So he has plus B3, which would be like rho cubed. Okay, and he says B3 equals B2 times gamma, meaning you have B2 would be like the binary interactions. And then he's saying, like, if I add a third one, then it's gonna, this influences that, will influence that by this factor gamma, which is 0.25. He gets that from another paper. Right, there's this other paper. That business comes from, like, I think this paper by this Noda guy from Japan. Right, where he talks about the same thing. So you know, that's you can link to that paper in there. Right, so he's going for the third viral coefficient. So he uses this expression where he's reduced this rho hat is rho molecular weight B2. So rho molecular weight and B2. So he's taken this thing, this whole thing is rho hat. Right, and then he says that this thing's going to be rho hat squared. I mean, this should be 2 because there's already a row here. And then the B3 rho hat squared includes B2. So B2 gamma, he's got to throw in a gamma there to get B3. B2 gamma is B3. Right, so that's what he does. He uses this expression, and he cites these papers that kind of use this same approach. It's easier because you have one parameter, just B2 to calculate, and the gamma uses a fixed number, dimensionless zero ratio. Whereas B3 over B2 equals 0.25. And then, all right, so that's the approach he's taking to model this thing, and then he uses that to get his this. So you can say that they look like stars. So when the composition, when the density goes up, and then this equals 1. Okay, so what is that? So when B2 times rho equals 1, that means you have B2 is by the van der Waals, it's the excluded volume, and then minus this attractive potential, minus A by T. Right, so it's like you have a sphere, and then there's some kind of maybe added. If it's repulsive, then it's added. Then you add in some kind of extra volume to it associated with A by T, or if it's attractive, you subtract off some volume associated with A by T. So your effective volume is this B2. Right? B2 is kind of the effective volume of the thing you're looking at. So if you say B2 times rho, that means you're basically have these things packed. That's basically rho star. Rho star is, that's the overlap concentration, is where like B2 equals 1 over rho. B2 equals 1 over rho, you're at this rho star for this kind of effective particle. Right, but that's not what he's using. He's using B2 rho. And this rho is based on the beads that make up the gel. So each of these beads that make up a gel, that's what this rho is based on, like how many beads. So if you take the number of beads times MW, that gives you the kind of the concentration in terms of the blobs, right? So anyway, if you multiply this by B2 times, that's where B2 is per blob. And then B2 rho times MW gives you per bead. So where it's 1 is where the beads, so where you have overlap of the beads. And where B2 rho is 1 is where you have overlap of the cubes. Right? Where rho B2 is 1 is where you have overlap of the cubes that we saw here, like rho over rho star, that's overlap of the cubes is 1 here. And this would be like overlap, because it's times molecular weight, overlap of the beads. When you get overlap of the beads, then you get to this thing. So somehow, right, even though they can't interpenetrate, somehow when you get to concentrations where you would be, so as you get higher and higher concentration, you're looking at smaller sizes. So at some size, you're going to start to see that a star polymer and this network polymer look the same. Like if I get to size scales like that, then the two things are equal to each other. Right? So you can't tell the difference because you're at a size scale that's smaller than the entire blob. So the entire blob size scale would be way down here because molecular weight's 100,000, so 10 to the 5. So it'd be like way down here somewhere would be the actual blob overlap. And then it's not until you get to the bead overlap that that you see that the stars are the same as the network things. It's a little bit like maybe it doesn't matter, but basically that's kind of what he's trying to show here. All right, there's that, and then there's a couple other things he does here. I just want to mention it. This isn't in the homework, but he calculates. So this is a Fourier transform. So okay, so exponential of I times some number, right? It's going to equal sine of the number minus I cosine of the number. Okay, so sine is basically a sine wave, right? I cosine is kind of like, you could think of it like electric and magnetic field. It's almost like talking about a wave equation. Out of phase by 90 degrees is a magnetic field, and then the electric field's in phase. So anyway, so this exponential I theta is going to be basically a sine wave, you can think of it, right? So if you look at across different wavelengths of the sine wave, then you're talking about breaking down something into different wavelengths, right? And you're summing those together with this double sum. So you're basically taking some odd shaped function and converting it into a series of sine waves of different amplitude, and this S of Q be the amplitude at this Q vector. So this is called a Fourier transform. Fourier transform the spatial position of the atoms to get the structure factor, which is what you see when you shoot a beam of light through it, the scattering pattern. So he can, because he's got the position of all the atoms, he can calculate the scattering pattern. Then he fits it with this power 2 means it's two-dimensional, so it's a Gaussian, power minus 2. So this is like the mass, that's 1 over the size. So 1 over the size goes with mass to the power 2 means it's two-dimensional. So that's a kind of a Gaussian scaling. So he says he's going to fit it with that, and then he puts in some factor at the front that takes care of large-scale fluctuations, just a power law function. So he fits these things. The problem is that if you look at this plot, so if you say 1 decade by 1 decade, so that's power 1, power minus 1 if you go like that. And that's exactly the slope he has here is power minus 1. Power minus 2 would be like twice that here, or half here. So power 2 would be really steep here. And that's not what he gets out here. So basically, this function isn't anywhere close to what his result is, and the result doesn't match at all what he has, because he's saying that this is a 2.5 dimension, so the slope here should be even steeper than 2. Should be 2.5 dimension out here, and it isn't. And this tailover is his radius of gyration. That's an exponential. That's the Gaussian decay, so the Gounod's law. So anyway, there's that business here, and he also sees this thing that the intensity drops with concentration. So basically that indicates that he's got, you can measure the second virial coefficient from that drop. He doesn't do that. What he does is he calculates the compressibility factor, which, see, it's a d pi d rho, which since pi as a function of rho gives you the B2, from that you can get the second virial, but he doesn't do that, he just gets this compressibility. He says the compressibility that he measures matches an experiment he did in 1988 or 1980 something. That other reference here, this thing from 1986 when he was in Budapest. Right? He did a measurement. He gets this power 3, power 6 as a function of solvent quality, and he gets the same power 3, power 6 as a function of solvent quality. And this thing, so he says that this verifies what he did. Anyway, I didn't ask questions about that, but so let me just go through the questions here. So here's the following equation to calculate. So at the beginning, he uses this thing. Okay, so this seems to be a little confusing. So what page? It's right at the beginning. It's at the end of something. Models and methods. Where does he say this? Right here. So on page, it's on page 6281, right? So he says, atomic pressure of the system is calculated from the Viral equation. So this doesn't look like our Viral equation, right? So it's like, what's going on with this thing? That's the question. So, all right, so we have from this other thing, from this guy, we have the B2 is this integral, right? So B2 is going to be the integral of this exponential of some potential function of position KT minus 1 times r squared dr, right? And this gives a volume, right? And then all right, so we got that thing, right? So he's saying that pi equals rho kt. So that's basically what we had before. That's ideal. And then plus w over v. And he doesn't say what v is, because w is the sum of the pair potentials, which equals rij and then du of rij over drij. Right? And then the u thing he's using is the u that he describes the potential somewhere here. He's got all these potentials. It's this potential. Another thing is that he calls potential v, and then he uses v for volume too. So he's got, when you write a paper, don't use the same symbol for two different things, like if you can help it, because it leads to confusion. Anyway, so this w is from that. So the question is like, what's going on here, right? So this is kind of how do you get this? So w is this thing. So this is our potential functions that we have. So this is so the derivative of energy with distance is going to be the force times distance gives energy, right? So these w's are pure Viral function, are really like energies of interaction at a specified distance, right? A fixed distance rij between particles. So we have the potential function that goes through r, like all r. We have a fixed r for our actual position of the atoms. So if we take the derivative of that potential as a function of r and then multiply it by the actual position of the atoms, so derivative at the position times the actual position gives you, so force times distance gives you an energy, the actual energy. See, the things are moving around all the time. So you need, when they're actually at some position, rij, what's the energy? And that's this energy. So we sum up all those energies, and that gives w, this big W, which he calls the Viral, internal Viral, right? So anyway, once you have w, then you say like, if you compare the two equations, so if you say rho kt plus rho squared kt b2 equals pi, the pressure. This is ideal. This is the second Viral. Then you compare it with his rho kt plus w by v, right? Then you can say that w equals rho, let's see, w equals rho squared kt b2, right? And then this is by v, so it's times v, right? So so then what am I getting to here? This is the integral that gives you w. Oh, and then b is this integral. B is the integral of b is this integral here. If this energy is small, you can say exponential of x equals 1 plus x squared plus x cubed by 2 by 6. And then, so if you just take the first term, if x is small, then this thing becomes 1 plus that potential number. And then we have minus 1. So just this, and it's negative. So that means that the negative here cancels out. So B2 just becomes this potential number if by KT, if B2 becomes a potential by KT if the potential is small, right? So just by expansion of the exponential, and you can do that. And then basically, if you plug that in here, then you get the same W thing that he has. This works out if you put that potential in here. Oh, because this is potential, and then it's times volume. It's that potential integral, and it's by KT, so that's unitless, and B2 becomes volume because it's a volume. Then if you plug this in wherever that thing is, wherever I wrote that here, B2 times volume. So then B2 has actually got volume in it. So this works out like that volume cancels his volume here for the W volume, and then you end up with the same answer. So it's pretty involved to get that, but basically try to do that if you can. It's based on this, and then I think you need the exponential expansion to work out exactly where this thing came from. This kind of comes out of the blue and he doesn't use it again, but it seemed to be worthwhile to kind of figure out what he was talking about. Then top of blah, 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 function WRI, how's W related to second zero coefficient? So you can kind of fumble around in that. Determination of the theta point. This I went through Kremos, the two methods to get the theta point, right? One is the matching up the RG molecular weight scaling part, and the other is calculate V2 and then find where it goes to 0. And then the axes, I went through those, what the axes are. I give some hints in page where things are. Freud-Krieg-Baum equation predicts this business, and then equation 4 uses that weird tan H hyperbolic tangent function. And similar to class, show how Krieg-Baum is obtained. So that's from the notes. That's from the notes in the PowerPoint for over here. That's kind of like, so when you obtain the Floyd-Krieg-Baum, the first step you do is you say you have ideal, and they do a perturbation to it. So you never have ideal here, you never have power 2, so this function shouldn't work for this. Although he ends up with the same functional form. So the Gaussian part is basically the first step. And then also, I think it's the only place you use Gaussian in this, so basically that's where the deviation comes into play. In the Floyd-Krieg-Baum derivation, the first step. First use of the Floyd-Krieg-Baum, at what point of derivation is it inappropriate for gel? The first step. And then plot against define RG. So that's this integral thing from the slides number 3, whatever that I showed you. How's it related to end-to-end distance? So it isn't like there's no end-to-end distance for a gel. That's the point of it. So you need to use some number, and RG is the only number you have. But it isn't the right number, it's too small. And then this, I went through this. What's rho by rho star equals 1? What is it? And in the power 1/3, I did that. And figure 8. So I went through this too. Like, what are the axes? Where do those things come from? The y and x axis. What's the meaning of that equals 1? I went through that. Why would this plot look like if only the second viral? It would be linear. It would be power 1. This is this figure 8 thing. So if this was a linear chain, then it would follow that dash curve, flexible chains, and that's a slope of 1. So log, so it's 1 decade by 1 decade. That's that slope. Like if you drew a line 1 decade by 1 decade, that would be the same slope as that thing. And then the other one's like 3, I think, the one for a solid spheres. High concentrations, well, the gel particles look like stars. So that's the thing about zooming in. Like if you go to higher concentrations, you're zooming into smaller areas in a star. The gel looks like a star when you zoom in like that. So anyway, it's a lot of stuff in this. It's kind of lengthy. I think after you get done with this, you'll either be completely confused or you'll have a pretty good handle on some of these things. And I'm going to go through these again. So we get another hit at this thing. But he does cover a lot of things that we covered in the class. They're kind of piled into this paper, so it's kind of useful to look at it. I think it's last year, middle of last year or something, May 2022, or I guess published in the summer. So, and it's good to see, like, know these names of people like Jack Douglas and this Jorge. Jorge is like Mr. Gel, and Douglas is a pretty famous guy too. So they're good. And then Bassler, I heard his name. I think he might be kind of famous too, but anyway, so it's good to know the names of the people. So you see a paper by Douglas, you know, it's a pretty good quality, or Jorge, it's kind of a good quality paper, you know, to pick up on. So anyway, any questions, anything? We had a couple of minutes, but. It's kind of it's a lot of stuff. So anyway, and we're not doing the tour today because I tested positive yesterday morning. So I thought, anyway, then Ryan, when I told him I tested positive, he said 24th of February. It's like in 3 weeks or something, you know, so we have to put it off for a little while. Sorry about that, but it's like, I don't know, it isn't right to go in if I got positive test. But I should be in on Monday, I hope, you know. So any comments or anything about this thing?
No, any, Prof, I saw that the question is like you updated the questions.
Yeah, I updated the questions.
Yes, yes, I do that. Yeah.
Yeah, I updated the questions. So I went through them and they like A didn't make sense.
Okay.
I had to redo A. And then I added in some stuff. I added in something about define the axes in this thing. Hopefully it's all there. If not, email me and ask a question about it, you know. If you're totally lost, it's okay, but try to go question by question. Like, I don't have any idea what you're talking about in A. This equation doesn't make any sense. Like, what, you know, something like that. Like, don't just say, explain the entire quiz for me. Yeah, because it's hard to answer that. I mean, without doing the whole quiz. So, but hopefully you can kind of feel your way through this. I mean, yeah, anyway, so just see how you can do on it. I think it's a good to jump into it. This thing, like if you work through this, you have a pretty good handle. If you can answer those questions about this, you got more than a good handle about like what's going on in osmotic pressure, the scaling stuff, kind of the simulations. There's quite a few features to this that are useful. So hopefully that's all right. But, okay, so have a good weekend, I guess.
Okay, Prof. Thank you. You too. Get
Thanks.
well.
Right,
Okay,
bye.
sure.